This lesson is on related rates. In class, we did a demonstration on related rates. Today, we're going to focus a little bit deeper onto what it means by related rates. So, many things change with time. Our goal is to find the rate at which some quantity is changing by relating the quantity to other quantities whose rates of change are known. Our strategy to tackle these problems are we're gonna read the problem and then draw diagrams, identify what you know about the problem, identify what you want from the problem, identify how the two are related, and then differentiate your related equation found in step 4. Plug in the appropriate information and solve for the desired quantity. This diagram shows a couple of different rates. The rate at which water is flowing out and the rate at which the water level is rising. So in a related rate problem, you will know one of these two rates. Perhaps they will give you the rate at which water is flowing out of this pipe, and then they want you to find how fast is the water level rising. That would be a calculus problem. Now, things change over time. So from now on, we're not gonna use the letter X. Instead, we're gonna use the letter T. Most of these problems is gonna involve implicit differentiation, so we're gonna be doing that a lot. So keep that in mind, okay? So some of these notations, these are first derivative notation. This first notation represents perhaps the change in the area over time, the change in the circumference over time, the change in volume over time, dv over dt, dx over dt, the change in y over time, the change in z over time, and so on and so forth. So here's your first problem. Y equals to x squared minus 3x. From now on, y is a function of time. Y changes when time changes. X is also a function of time, guys. So these are two functions together. These are function of time. So the first thing they will ask us to do is they ask us to differentiate this function with respect to time. So first, because they're with respect to time, why don't you write it like this? And it might be helpful to write it like this. All right, these are functions of time now, guys. Differentiate with respect to time. We're gonna go ahead and differentiate both sides implicitly. The derivative of y, we call that y prime, right? So y prime like this. The derivative of x, it's 2x times x prime. Okay, because it is with respect to time. And the derivative of 3x is 3x prime. So I differentiated with respect to time. And now, here's what they want us to find. They want us to find the derivative of y with respect to time when x equals to 3 and x prime equals to 2. So we just need to take this data and we plug it in to the appropriate value to find that. We're looking for this because that's what dy over dt is. So dy over dt, that's what this is 2 times x of t is 3. Okay. X prime is 2. This is x prime. Minus 3 times 2. That's x prime. And if we do that correctly and multiply everything together, we get 12 minus 6. That is 6. So the change in y with respect to the change in t is equal to 6. 12 minus 6 is 6. All right. Find x prime. This is x prime. When x equals to 4 and dy over dt equals to 2. This is kind of like a related rate problem. You're asked to find one rate when you're given another rate. That's a related rate problem. So this is your main equation that we're always going to refer back to. Okay, we're going to plug this in here and then replace x with 4 and try to solve for x prime. So 2 equals 2, x is 4. We're finding x prime. This equals to 8, x prime. And that equals to 5x prime when you subtract. So x prime is equals to 2 over 5. That's the rate of x prime. Okay, here is another problem, and this is a beginning of more concrete related rate problem. Let's start with a simple problem. The side of a square is changing at a rate of 2 inches per minute. So as time goes by, the size of a square is getting larger and larger and larger, 2 inches every minute. How fast is the area changing when the size are 3 inches? So we go back to the basic strategy of solving a related rate problem. Identify what you know, identify what you want, and then identify how the two are related and then differentiate. Okay, so here I'm going to start by writing down what I know. So what I know is that the size are increasing at a rate of 2 inches per minute. So because it's a rate, we write it as the first derivative, the change in side. The change in the side length with respect to time is 2. Okay. And what do we want? Okay, what we want here is we want to find, so we know a rate and they're going to ask us to find another rate. So the rate that they want us to find is the area. How fast is the area changing? So the change in area with respect to the change in time is what they want us to find, right? And they also give us an additional information. Find this when the size are 3 inches. So the size, let S represent the size, so S equals to 3. Put that under what you know. What you know, what you want, and then how they are related. How the two rates are related. How is the side relate to the area? Well, we know that area is side square, right? That's area. But remember, we're trying to find their rate with respect to time. So we write the area function as a function of time. Side is also a function of time because as time passes, the side is increasing 2 inches per minute, right? That's what it says. So write it as a function of time, and then now we write what we wrote down how these two rates are related. Now we differentiate. So the derivative of A, we call that A prime, right? A prime. And the derivative of that is 2s times s prime. Okay, relate, differentiate. And then remember that you're trying to find the derivative of the area, the change in the area. Well, here it is. That's what you're trying to find. So leave that alone. You plug in what you know, and you calculated the change in the area. So the change in the area with respect to time is 2 times 3 times 2. And that equals to 12. So the change in area with respect to the change in time, when s equals to 3 is 12 inches square per minute. So when the length of the sides are 3 inches, the area is increasing at 12 inches per minute. Okay, good. Here is in the second part of the first problem, using similar data, using this first data here. This is first information that we know. So the size of a square are increasing at 2 inches per minute. That's what we know. The change in the side with respect to the change in time. It's a rate. And what we want is we want to know how fast the area is changing. So the change in the area over the change in time. We want to know this when the square has an area of 25. When the area equals to 25. Now, common sense will tell you that if area equals to 25, then that means that each side must be 5, right? Because that's how area of a square equals 25. So even though they did not specifically give us this information, but we were able to extract that from the area, and that was just using common sense. Now, how are the area and the size related? Same as before. Area is equal to s squared, but area is a function of time, so make sure you put t there. The derivative, take the derivative of both sides. Okay, same thing as before, I'm just using different notations. Okay, don't be scared by that. We want to find this out, so we plug in the other information. So we conclude that change in area with respect to time when the area is 25 is 20 inches square per minute. So exactly when the area is 25, the area is increasing at 20 inches square per minute. Awesome. The radius of a circular oil spill expands at a rate of 3 meters per minute. This is like a circle, right? So as oil spills, the circular coverage increases at a rate of 3 meters per minute. The question here is, as the radius increases, how fast is the area increasing? So what do we know? They always tell us a rate. So read the problem. You know that oil, the radius is expanding at 3 meters per minute. So the change in the radius over the change in time is 3. What do we want? We want to know how fast is the area increasing. How fast is referred to a rate, okay? So they want to know how fast is the area increasing. A stands for area. When the radius is 45. So when r equals to 45. See? How are they related? Area equals to pi r squared. But please keep in mind that from now on, especially in related rate problems, things are changing with respect to time, so we always have to use t as our variable, and then we have to differentiate this. So the derivative of a of t is a prime, and that's how we write a prime. The derivative of the radius, differentiate both sides. The derivative of the radius, bring down the 2. Leave that alone, and then multiply it by its derivative, which is r prime, but we use the symbol for r prime. And then we plug it in. We plug in what we know. And we're gonna get, seems like over 100. Okay. We are going to get 270 pi. So we're looking at the change in the area with respect to the change in time when r equals to 45 is 270 pi meter square per minute. Okay. So exactly when the radius is 45 meters, every minute the area is expanded 270 pi. 270 pi is 848. A pretty big amount. Okay. All right. If the radius of the spill is 0 at time 0, how fast is the area increasing after 5 minutes has passed? So here's what we know. We know that the change in radius with respect to the change in time is 3. Here's what we want. How fast is the area increasing after 5 minutes? So time equals to 5 minutes. How fast is the area increasing? How are they related? From previous problem, we know that the derivative is this. Okay. But what is r? What is r? Okay. Well, if we read the problem carefully, we know that at time equals to 0, the radius is 0. Okay. 5 minutes later, guess what? 5 minutes later, the radius should be 15. Why? Because the radius is increasing 3 meters per minute. If it began at 0, then 5 minutes later, then it should be 15. See? So sometimes you have to use common sense to come up with another information that you need. Plug those in there. Um, 30 times 3, 90. Our unit is meter square per minute. Okay, there you go. And then the last problem here. Water is draining from a cylindrical tank at 3 liters per second. How fast is the surface dropping? This is kind of like a problem that we did in class. There's a nozzle, right? And water is coming out of this nozzle. And it's coming out of this nozzle. 3 liters per second. So the question is, how fast is the surface of water dropping? Those two, so we know this one rate, and we're asking to find another rate. So let's write down what we know. What we know is the change in volume with respect to the change in time is 3 liters, because this is the draining is removing the volume. Okay. What do we want? We want to know how fast the surface is dropping. So we want to know the surface is really talking about the height. So the change in height with respect to the change in time. That's what we want. How are they related? Volume is equal to pi r squared times h. That's how volume and height are related. Okay, remember, volume is going to change as a function of time. Here's a question. This is the radius. As the water level is dropping, does the radius change? And the answer is no, the radius doesn't change. So the radius is not a function of time. The radius is just a constant. It does not change. What changed? The height changed. So that's why the height
Hey guys,
is a
r
function
should
of time.
be squared, so make sure you
So
put a
now
square
we
on r
differentiate
for
both sides.
the next few steps.
The derivative of v is called dv over dt. Take the derivative of h, leave these two alone. So pi r times h prime. We want to know h, we want to find h prime. This is h prime. Plug in what we know. So we know that this is 3. Okay. This is pi and this is r. Times h prime. Okay. So h prime equals to 3 divided by pi r. So the height is changing at a rate of 3 over pi r, whatever r is. We do not know what r is, so therefore we have to express our answers in terms of r.